Let's talk real quick about ion channels and how they pertain to the action potential. Here, let's start with mentioning the sodium channel, the potassium channel, the calcium channel, and the chlorine channel. Let's look at the sodium channel first. We can see that this sodium ion fits snugly. It's a good filter pore for the sodium channel, for the sodium ion, since no other ion can go through here, since sodium ion is one of the smallest ions. Potassium ion wouldn't be able to enter because it's too big. However, potassium ion can enter through its own potassium channel because it has enough of a gap for it to enter. Plus, it's also attracted to these uh, oxygen ions that we can see around it, which is the protein of the membrane of the channel. And sodium ion could enter through here. However, it does not have the thermodynamic conditions appropriate for it to enter, so it is often rejected. Same thing with the calcium channel. It will be able to reject other ions from entering, even though the gap is big enough for other ions to enter. We can also see with the chlorine channels, they are able to be selectively filtered through because the protein has actually positively charged areas so that only negatively charged ions can go through, like chlorine. Now, let's go a little bit more in depth. So, here we can see that we have a potassium channel. It has three different mechanisms. It can be activated and closed, activated and open, or inactivated, where there is a ball that closes up the whole channel so nothing can go through. Let's see how this pertains to the action potential. We have resting memory potential, that's -70. Let's say we get a current that depolarizes to the threshold, and this is the sodium channel's threshold. So then once we reach -50, we can see that we have now activated. The gate has closed, sorry, the gate has opened and it's been activated. So now we can see a bunch of sodium ions rush in. And then at this point, at the very peak, we can see this inactivation where nothing else can go inside no more. Now let's take a look at the potassium channel. We can have two mechanisms, either closed or open. Let's see how this looks in the action potential. So once we have depolarization upon reaching the threshold, we can expect to see potassium channels opening up around, let's say, -40 millivolts of voltage. And they're very slow, so you won't necessarily see much of an effect until the very peak where sodium channels are absolutely inactivated, and so potassium channels are taking over and leading the charge of repolarization all the way down. We should also talk about calcium channels, which are very important for the actual transmission of the signal to others, to other neurons. And we can see that it can have a closed state or an open state. And we have a threshold of around -30 millivolts. So at the very end, once your action potential reaches the axon terminal and it maintains the signal at a good current enough to completely depolarize the threshold, then we can expect to see synaptic transmission.